Hi, welcome back to McClutchy Maths. My name is Natalie McClutchy and today I'm continuing our video series on sequences and we are going to do an introduction to geometric sequences. And I'm aiming this video at students right across Australia in our senior maths strands, depending on where you are and what it's called, grade 11 and grade 12. Now in this video we're going to cover a few different things. We're going to look at what a geometric sequence is. I'm going to show you how to prove that a sequence is geometric. We're going to talk about recurrence relations, how to write them, how to use them and when to use them. We're going to look then at a general rule, and this is usually on your formula sheet in your state. And then we're going to show you how to use the iterative function on your calculator. And finally, we're going to show you what a geometric sequence looks like when it's graphed. So this video is jam-packed. You're not going to want to miss this one. Okay, so firstly, let's talk about what a geometric sequence is. We've talked about arithmetic sequences that increase and decrease by a common difference, the same fixed amount every time. But in a geometric sequence, we are looking at a series of numbers that increase or decrease in what's called a fixed ratio. So instead of increasing by 2 or 3 or 4, we're now going to be using a multiplicative relationship between the first number and the next number and the numbers into the sequence. So here is an example of what that could look like. 1, 2, 4, 8, 16, 32, 64, 128. Now if you tried to apply your theories about arithmetic sequences to this, you would notice that there is a difference of 1 between the first two, a difference of 2, and then a difference of 4. So it's not going up by a fixed amount. However, if we take that second term and divide it by the first term, we'll see that what's actually happening here is that it's doubling all the way up into the sequences. It's being multiplied by 2. We've also got another example here, 100, 50, 25, 12.56.25, and the same sort of principle applies. It's not decreasing by a fixed amount, but we've actually got a halving thing that's going on here. It's being multiplied by 0.5 all the way along. So instead of adding, we are multiplying or dividing. So this fixed ratio that is multiplied by the first number to get the second number is called the common ratio. And we represent that with the variable r. And it would look like this if we used some of our different algebraic representations. So I'm taking the second term, t2, I'm dividing that by the first term, and that's going to be equal to the third term divided by the second term, and the fourth term divided by the third term, all the way up until you get to the last term, which is divided by tn minus 1, which is the term before the last term. So let's do some worked examples with this. Firstly, we need to be able to prove that a sequence that has been given to us is geometric. And the working and the setup for this is quite important. If you're doing an exam and you're asked to show or prove or demonstrate, then it's really important that you set it out properly so that you don't lose any marks. So firstly, we're going to use that basic algebraic form. This is often not awarded marks for doing something like this, but you do at least need to show the substitution. I think if you're in methods, you probably would, however, need to show the rule for how a geometric sequence is set up. So being able to show that using algebra is important. So let's substitute from the series that's given to us in the worked examples. 5 divided by 1 is equal to 25 divided by 5 is equal to 125 divided by 25. And the common ratio for all of those is 5. Now, if you were given more numbers, you should use all the numbers to prove that the sequence given is geometric, not just take a select couple. And I often see students taking a shortcut. They'll just take the second number divided by the first number and say the sequence is geometric. But what if the third number and the fourth number didn't follow the pattern? And sometimes that could happen, especially when you're using real life data. So you need to use every term in the sequence to show that that sequence you're given is geometric. So we also need to write a therefore statement at the end and not just leave some numbers randomly on the page. So I've got a little statement here, therefore the sequence is geometric because it has a common ratio of 5. So we've got the statement that it's definitely geometric, but we also need to have our reason why. And the reason is because there is a common ratio and we've stated that it's 5. So that is complete working for a proof. Okay, let's talk about the recurrence relation that we would use for a geometric sequence. And you recall from previous videos that recurrence relations have 3 main parts. We've got information about what that first term, T1, is. We've also got an equation. And when I say 3 parts, every equation has 2 sides. There's an equal sign that separates the 2 sides. And that equation explains to us what actions are being performed on the nth term to reach the term after that, which is term n plus 1. Now, you would also recall, if you're especially in Queensland, that we don't give you the recurrence relation for an arithmetic or a geometric sequence on your formula sheet. So this is something you need to be able to memorize. It's also something you need to be really careful when you're reading a question. If you're asked what's the general rule, then you pull your formula sheet out. But if you're asked to provide a recurrence relation, or if you're asked to use recursion, then you're going to need to use this form. And I often find that's a mistake that students make, is they don't read the question carefully and they jump straight to the general rule that's on their formula sheet. They don't understand that there's actually a difference. So for a geometric sequence, our recurrence relation is in the form of the first term is equal to the letter A. Your formula or textbook may use a different variable, that's okay. And then we have our two sides of the equation. Tn plus 1 is equal to Tn multiplied by R, which is our common ratio. Like I said, your formula sheet in a different state to Queensland might use some different variables, but the principle is the same. Now, our common ratio, something to be aware of, it could be a whole number, it could be a positive number or a negative number, it could be a fraction, a decimal, or a percentage. So it can be given to you in different ways. So you may be told that it's not a geometric sequence. You just may be told that the sequence is increasing by, for example, 8% per annum. And if that's not 8% of the first term, but 8% of every term in the sequence, then it's a geometric sequence. Let's look at another worked example. We're going to use the information that's given to us in the recurrence relation to generate the next 4 terms. And this is often a simple familiar question on exams. So we're told that the first term is 3, and we're told that our common ratio is 4. So we just need to do the next 4 terms after term 1, which is 3. So let's start with writing term 1 equals 3. Now we know we've got to multiply the number 3 by 4 to get to the second term, which will give us 12. And then we're going to take 12 and multiply that by our common ratio 4 as well, which will give us 48. Then we take 48, that will give us, when we multiply by that, 192, and to our last term, term 5, which will give us 768. So that's fairly straightforward, pretty easy on the calculator to do that kind of working. And we also should write a statement at the end, because the question is a worded problem and it doesn't refer to T1, T2, etc. So we're going to write that down. The next 4 terms in the sequence are 12, 48, 192, and 768. Now, we need to be able to write that recurrence relation and understand why we would be using it. Now, a recurrence relation does have limited usefulness. It's really only useful to be able to generate the next term or the next few terms. It's not great for predicting all the way into the future, such as to find term 30. You certainly wouldn't want to do working for 30 terms. And so we need a general rule, and that's what's on your formula sheet. And it looks like this. The term n is equal to the first term multiplied by the common ratio raised to the power of n minus 1. Now, I often see students making a mistake and they forget that it's a power, and they're not looking at the fact that it's superscript, which means it's got an index, and so they multiply it by a number instead of raising it to a power. So that's a really important distinction to make. So our first term is multiplied by r, and it's r that's actually raised to the power. Another common mistake I do see is people not knowing the order of operations. Remember BIMDAS? So the first one's brackets, well, there's none of those here, and then I is indices. So that means we're raising the ratio first to the power, and then the m for BIMDAS, we multiply it by the first term. And that common mistake I see people making is that they multiply term 1 by the ratio first and then raise that to a power, which is not what we're doing unless it's in brackets. Okay, so let's do this with our third worked example. Let's find the 18th term of the geometric sequence, 3, 6, 12, 24, 48. Now, obviously in this situation, we don't have to prove it's a geometric sequence because we're told that it is. And so we know we can jump straight to our general rule, because I often find students are a little bit confused. Should I use the recurrence relation or should I use the rule? Well, we're not being asked to generate the first 18 terms. Thank goodness. If that was the case, we would use recursion, but we want to jump well into the future and find the 18th term, so we're going to use our general rule. So firstly, we've got to work out what that common ratio is, and because we've been told it's geometric, we know we're looking for a ratio, so we're going to do that taking the second term and dividing it by the first term, and we'll get the common ratio of 2. Now we're going to state our variables. The first term is 3, the ratio is 2, and we've got n equals 18 for 18 terms, and we'll substitute that into our rule that's from our formula sheet. So if we do that, we've got the 18th term is equal to 3, our first term, multiplied by 2 to the power of 18 minus 1. Now we know 18 minus 1 is 17. So it's really important that we do it on our calculator backwards. You're going to actually raise 2 to the power of 17 first and then multiply that by 3, and then you'll get the answer, and you're going to write a statement. The 18th term is 393,216. Now you might be a little bit freaked out by the fact that it's so far from 48. You would expect it to be, because we've got this multiplicative factor happening here that it's like a power of compounding. So we go quickly from 3 all the way up to 393,000. And you would expect that. If you had a number that was smaller than 48, a number that was negative, or a number that wasn't very big at all, you'd be asking yourself questions, because this is the power of compounding. Let's look at another worked example. I see this a lot in textbooks. They really like the ball dropping and the rebounding. So let's talk this one through. A ball is dropped from a height of 200 centimeters. Its first rebound is 108 centimeters, then 58.32 centimeters, then 31.49 centimeters. Use a recurrence relation to find the fourth and fifth rebounds, and an equation to determine when the ball's rebound height is below a centimeter. So there's a few things that this question's asking us to do. Now, one of the common mistakes that I see people make is to see the word first rebound and to think that's the first term. It's not. Our first term is actually the height that it's dropped from. So it's dropped from 200 centimeters, and then it hits the ground, and then it bounces back up to 108, then it bounces back up to 58.32. So the first rebound is actually term 2. And that's one of the little mistakes people make. So we've got to be careful. Our starting height is term 1. So firstly, what we're going to do is write the recurrence relation. That's the first thing that our question is asking us to do. And I've highlighted that in yellow because there's a few parts to this question. So let's write that recurrence relation. We'll get our basic form together first. That should be in our memories. And then we're going to substitute our information in from the variables that we have. Term 1 is 200. The common ratio is 0.54. Now, I probably should show some working of how I achieved that as well. 108 divided by 200. Some students do make the mistake of doing term 1 divided by term 2. I did see that in an exam recently where they put the wrong term on it as the numerator and the wrong term as the denominator, and they ended up with a factor where the recurrence relation started to increase instead of decrease. So it's very careful. Term 2 on the top divided by term 1. Okay, let's substitute that into our relation. So now we've got a recurrence relation from our basic form. We're going to use that now to find those fourth and fifth rebounds. So term 1 was 200, and the next two terms is, we've got term 1, term 2, term 3, term 4, but the fourth and fifth rebounds is actually term 5 and term 6. So we're going to substitute T5 into the equation. N is going to be equal to 4 in the right-hand side of the equation. So term 5 will be 17 centimeters and term 6 will be 9.18 centimeters. We're just multiplying that last term by 0.54, and then we do it again. That's how we can use recursion to find the next few terms. Okay, so that's the first part of our question completed. Now we need to use an equation. So we're now jumping away from our recurrence relation. We're going to use our general rule to find when the ball's rebound height is below 1 centimeter. Now to do this, I'm going to have to substitute some information into the equation first. So I know that the height I'm looking for, my last term, is going to be 1 or below 1. And I know I'm going to start with my first term, 200. I'm going to multiply that by 0.54 raised to the power of n minus 1. Now I don't know how many times it's going to bounce. I need to find n minus 1. And this is a problem because I don't know in general maths how to find a power when it's all by itself. Now, if you're in math methods, you're going to want to use logarithms. I'm going to show you today how to use the calculator to find this with the iterative function. So firstly, we're going to divide both sides by 200, and that leaves us with 0.005 when we evaluate that on our calculator equals 0.54 to the power of n minus 1. Now, a mistake that I would see students doing here is divide both sides by 0.54, and then they've suddenly turned that index into just basic algebra n minus 1, which is wrong. Do not do that. N minus 1 is a power, so we need to actually evaluate this on the calculator. So let's do that. So what we're going to do is we're actually going to focus on this side of the equation, the right-hand side of the equation. So we're actually going to put 0.54 onto the calculator, and we're going to press the equals button. And that will drop it down from the top side of your screen to the right-hand side of your screen, which will enable you to use the iterative function. And I'm using a Casio calculator for this, a scientific calculator. So what I'm going to do is multiply that by 0.54. And if I press the equals button, I'm actually squaring 0.54 the first time I press it. So that's squared. That's to the power of 2. Let's try the power of 3, the power of 4. And we need this to be below 0.05. So let's go again, the power of 5. And now we're finally, oh, we're not quite there yet. Power of 6, power of 7, power of 8. Oh, almost there. And the power of 9 actually gets us below. So what we've found is that our ninth power, r to the power of 9, gives us our answer for when the ball's rebound height is below 1 centimetre. So if we now substitute that back into our algebra, we end up with n minus 1 is going to be 9. Now if we rearrange that, that means n is 9 plus 1, which means that n is 10. Now it's our 10th term is actually going to be the one we're looking for. Now we need to think about that in terms of rebounds. If our first term was 200 and our first rebound was term 2, then that means that our 10th term will be our 9th rebound. So let's look at the working for that and how that would actually look. So we're going to use our iterative function in the calculator. We've just done that. And we didn't need to write down all the previous terms because we found those. So term 7, term 9, and term 10, which means that our ball's rebound will be below 1 centimetre on the 9th rebound, which is our 10th term, which is the 9th power plus 1, n plus 1. Let's look at another quick worked example. We're going to use our iterative function again. The first 3 numbers of a geometric sequence are 1, 5, 25, and 125. Which number term will be the first to exceed 1,000,000 in the series? So first of all, we're going to show our working and find the common ratio, which is 5. We're going to state our variables and substitute them into our rule. And it would look like this. 1,000,000 equals 1 times 5 to the power of n minus 1. So once again, we're going to simplify that a little bit further, divide both sides by 1, and we're going to use that iterative function on our calculator again. So let's get that ready. Okay, so let's put 5 onto the calculator and press the equals button. And we're actually going to square it first. We're going to be multiplying it by 5. That's what a power does, multiplies it by itself. So the first time I press the equals button, I've got 5 squared. Now I've got 5. We're trying to get this past 1,000,000. 5 cubed to the power of 4 to the power of 5 to the power of 6, 7, 8, and 9 gets us past 1,000,000. So the 9th power gets us past 1,000,000, but it's not the 9th term. Remember, n minus 1 equals 9. So really what we're seeing here is that n is equal to 10. It's the 10th term. So we need to show some working for that. So I've got all of that information here now. I've taken it from the 6th term, the 7th, 8th, the 9th, and the 10th, and I've given all of that information, and then I need to finish it off in a statement. It's the 10th term that will be the first to exceed 1,000,000. So that's one little mistake that people will often make, remembering that it's the power of 9, but it's not the power of 9, it's n minus 1 equals 9. So therefore, n equals 10, and it's the 10th term. So be very careful when you're finalizing your answers off. Let's look now at how a geometric sequence looks when it's graphed. We can see that it's going to form a curve. It's called exponential growth in this case. And we see that the numbers start out and there's not a lot of change between term 1 and term 2 and term 3, but as the sequence goes on, it starts to move quite rapidly. And this could be a challenge graphing accurately if you're asked to do that by hand, because those first few numbers, you're going to have to basically guesstimate where they fit. If you've got a small piece of graph paper. One of the common mistakes I see that people making when they graph a geometric sequence is that they don't do their y-axis correctly. You'll notice here I've done it correctly, and the difference between each point on that y-axis, it's going up in a fixed amount, in 50s. Now you might think, well, hang on, it's a geometric sequence and it doesn't go up in a fixed amount. No, that's correct. The actual numbers won't go up in a fixed amount, but your axis should. Your axis should be scaled correctly. So make sure both of your axes have the correct scaling, and then you plot accordingly, and it should graph like a curve. And the same when we're looking at decline. It's actually going to be the opposite direction, starts up very high on that first term and then moves away down towards zero, and those last numbers get very close to zero. But something that should be noted is it will never actually touch zero. And kind of, because this has been graphed in Excel, it doesn't really show you the distinction there, but trust me, it's not actually on zero, it's a fraction. And because our scale on that y-axis is in 50s, it looks like zero, but it's not. Now, something that you really need to understand is that when you have geometric sequence with this exponential decline, because you're multiplying by the previous one. So let's say I started with the number 10 and I found half of 10. I had a common ratio of 0.5. Well, half of 10 is 5, and then I multiply that by half again, 2.5. Half again, I get 1.125. Half again, I get 0.625. And then if I continue multiplying by half, try it on your calculator, you will never, ever reach zero, because half of a number is going to be another number. It'll never be zero. So that's something very important to remember about a geometric sequence as well. If you're given a contextual problem, for example, I've seen ones where, for example, garbage, the amount of garbage or the amount of carbon in the atmosphere or the amount of pollution in the ocean, and it's declining in a geometric sequence, it's never going to reach zero because you're always multiplying a number by another number. Let's have a quick look at what's coming up. We're going to show you how to solve geometric sequences using simultaneous equations. We're going to talk about compound interest, depreciation, and population growth, which are all common worded problems that we see used with geometric sequences. We're going to look at the sum of a geometric sequence for our methods students, and then we're going to look at some complex questions from some past exams. And I'd like to say thank you so much to all of our new subscribers. We hit 900 this week and we're still growing, hopefully growing in a geometric sequence. So welcome to the channel if you've just joined us. Thank you very much for being here, and why not follow McClutchy Maths on Facebook. And if you've got any burning questions, the best place to ask is not in the comments, but to contact us at mcclutchymaths@yahoo.com or through Messenger on Facebook. Once again, I'm Natalie McClutchy. Thank you so much for joining us here at the channel. Have a wonderful day.